Okay, welcome ladies and gentlemen. So before we get to the definition of a limit, let's go through a more intuitive example just to show how quantifiers and predicates play with each other. So I am going to go through an example. Let us define two sets, and let us define the set M as the set of some male members of the British royal family. So Charles and Philip and William and Harry and little baby George. So this set M is the set of these men that I have listed, these male members of the British royal family. And W, I'm going to say, is the following set of female members of the British royal family. So Elizabeth, Camilla, and Kate, and Diana, and who's the new lady? Meghan. Okay, so here we have two sets, M and W, and let us define some predicates on these sets. So let us define some predicates. Let us say let us define the predicate mar. It has it takes inputs in the Cartesian product of M with W, meaning all possible pairs of men and women in the British royal family. And what should it do? It should evaluate to either a true or a false statement. And how do we define this predicate? Mar of M and W. We say, we define to mean M is married to W. So we see this is a predicate that depends on two variables. And let's define another predicate, little m, as we had before. Let's say, actually, let's write it this way. M, what is its input? It is the union of all men and women in the British royal family that we have defined in these sets, and it evaluates to true or false. And how do we define it? We say M of X is means the following: X is married. Actually, I'm going to rename this predicate. I'm going to call it a mar. Little mar. We've gotten capital Mar and little mar. I renamed it because I don't want to cause confusion with these M's that I'm taking out of the set M. And of course, capital Mar, that is defined for all MW, all pairs MW in the Cartesian product of M with W. And this is little mar is defined for all X. So for all X in the union of M and W. Good. And now we can, depending on what values these variables take, capital Mar, or big Mar, and little mar can take on or become true or false statements. So let's take a look. For example, mar of Philip and Diana. This is false because Philip is not married to Diana. But mar of Charles is Charles and Camilla. That is true because Charles is married to Camilla. Little mar, so mar of Charles, that is true because Charles is married to Camilla. But little mar of baby George, that is false. Baby George is not married yet. Okay. Now we can also make some quantified statements using these predicates. Let's look at the following quantified statements. So some quantified statements. Quantified statements. So let's say for every m in the set, and let's take a subset of our mem, Charles, Philip, and William, there exists a W in the set of all W, so that capital Mar MW is true. So this is a quantified statement. You see we've got this predicate here depending on the variables M and W, but each variable is quantified. So M is quantified with a universal quantifier and W is quantified with an existential quantifier. So this becomes a logical statement because all the free variables in your predicate capital Mar have been quantified. And now we can think of, is this a true statement or is it a false statement? So let's see. For every man, Charles, Philip, William, there exists a woman who is married to that man. And in fact, if you so in this case, how do you decide if this is a true statement or a false statement? You need to go through all the possible combinations. So for every man, so let M take on the value Charles. Is there a woman who is married to Charles? Yes, Camilla is married. And now you let M take on the value Philip. Is there a woman in our set W who is married to Philip? Yes, because Elizabeth is married to Philip. And you let M take on the value William. And you ask and we ask the question: is there a woman married to William? Yes, there is. Kate is married to William. So for every man, there exists a woman who is married to that man. Let's take a look at another example. So let's use the whole set M. So for every M in M, there exists a W in W, so that capital Mar or big Mar MW. Again, this is a quantified statement. All the variables in our predicate have been quantified, so this becomes a logical statement. And let's see if this is true or false. So for every man, does there exist a woman who is married there? And I claim that this is false because for baby George, none of these women listed here are married to baby George. So this is false. So there is not, for every man, there is not a woman who is married to that man. So this is false. Let us talk about negation. If you have a logical statement, so a statement that is either true, unambiguously true, or unambiguously false, its negation is defined as the logical statement which has the opposite truth value. So if you have a logical statement which is true, its negation is by definition false. Okay, so now how do we negate quantified statements? So let us take a look at this last statement that we had. It is false. That means that its negation should be true. So how do you negate a quantified statement? Let me write that down. How do you negate a quantified statement? Okay, very important. How do you negate a quantified statement? So a quantified statement is, or you negate it, you start at the beginning and you change every quantifier to the other quantifier. So every existential quantifier you change to a universal quantifier. And every universal quantifier you change to an existential quantifier. So you do that with all the quantifiers and you negate the predicate. So let us call this A. Let us write down the negation of A. Okay, A says for every M in M there exists a W in W, so that capital MAR MW. Let us negate A. So it says for every M, change it to there exists an M in M. We go on. Then it says there exists a W in W. Change it to for every W in W. And negate the predicate. So not MAR MW. Okay, let's see if we can understand this statement. So it says there exists an M in capital M, so that for every W in capital W, not MAR. So so M is not married to W. So let's put in brackets. What does this say? M is not married to W. Okay, and now if we think a little bit about this, this is of course true, because so there exists a male member of the royal family, little George, so that for every woman in this list, George is not married to that woman. So for every woman in this set, George is not married to Elizabeth, George is not married to Camilla, George is not married to Kate, George is not married to Diana, and George is not married to Meghan. So this then becomes true. So this negation of this previous statement that we have, previous statement we had was false, the negation is true. Okay. Let us take a look at another example. And now this will be a quantified statement that has an implication in it. So let's say for m in m, no, for every x in m, if mar x, if this x is married, then x is Charles, is equal to Charles. Okay, here we have a logical statement. We see here, over here we've got the predicate, depending on this variable x, and it is quantified with a universal quantifier. Let us see if this, let us think about if this statement is true. So for every man in our set of men that we are considering, if that man is married, then that man is Charles. This is of course false, because William is in this set, capital M. William is married to Kate, but William is not Charles. So this is false. This is false. That means the negation of this statement is true. The negation is true. So let us negate this statement. So let's call it B. The negation of B is true. What is the negation of B? Again, we're dealing with a quantified statement. So how do we negate quantified statements? You flip the quantifier, you negate the predicate. So we flip the quantifier. So we have a universal quantifier, we flip it to a existential quantifier. So there exists an x in M, and now we negate the predicate. So now be very careful. Here we have an implication. So we need to negate this implication. I'm going to down here. I'm going to show an example of how to negate an implication. So here we have an implication. If A and B are logical statements, if A then B, that is an implication. The negation of an implication is not another implication. This is something that you must get to grips with. What is the negation of an implication? The negation of an implication is not another implication. It is an and statement. So this is the negation of an implication is the following. So A is true and B is not true. Or in other words, A and not B. And here, notice the logical connectives, the and here and the negation there. So, if there is one thing that you remember from this little video lecture, it is that the negation of an implication is not an implication, it is an and statement. Say that with me now. The negation of an implication is not another implication, it is an and statement. Okay. So, let us negate this statement B that we were busy with. For every X in M, if X is married, then X is Charles. So, how do we negate this implication? We have, so for example here, A would be M of X. So, M of X and not X is equal to Charles, or we can write it this way, X is not equal to Charles. And here we see, let's take a look at this statement. Let's see if we can understand it. There exists a man in our set of men which is married. That man is married, but he's not Charles. And if we look at our set of men that we are working with, there are many of them that satisfy that condition. For example, Philip is a man who is not Charles and is married. William as well, and Harry. So let's see here. There exists a man, for example, Philip. Philip is married to Elizabeth, and Philip is not equal to Charles. Okay, so this statement is true. It is true, and its negation is false. Okay, so now let us reiterate here. Remember, the negation of an implication is not another implication. It is an and statement. It is an and statement. Okay, let us get to our last theme in this video. And also, very important, the order of quantifiers matter. So, whether you say for every something something there exists something something, that is different to saying there exists something something. So that for every something something. If you swap the order of the quantifiers, you change the meaning of the statement. Let's take a look at an example. So the only difference between these two examples are that the order of the quantifiers are swapped. But one is true, one statement is true, and the other statement is false. First example, for every M in the set Charles, Philip, and William, there exists a W in the set capital W, so that capital MAR MW. So let's think about this. For every man in this set, Charles, Philip, William, there exists a woman, so that that man is married to that woman. So let's think about this. Let's just go through all the combinations. So for every M, if M is Charles, there exists a woman depending on Charles, Camilla, so that Charles is married to Camilla. If M is Philip, there exists a woman depending on Philip, Elizabeth, so that Philip is married to Elizabeth. And if M is William, there exists a woman, Kate, depending on William, so that William is married to Kate. Let us see what happens if all that we change is we change the order of the quantifiers. So instead of saying for every M, we will say that we will swap these quantifiers. So instead of saying for every M in this set, we will first say there exists a W in W, so that there exists a W in W, so that for every M in our set Charles, Philip, and William, we have Mar M W. And just so that it flows nicely in English, let's add a so that in there. There exists a woman in our set W, so that for every man in the set Charles, Philip, William, that man is married to that woman. Let us think about what this says. This says that there exists a woman in our female members of the British royal family, so that every man in our set Charles, Philip, William, so Charles, Philip, William, that Charles is married to that woman, Philip is married to that woman, William is married to that woman. So what this statement says, there exists a single woman who is married to Charles, Philip, and William. That is not true. The British royal family are depraved, but they are not so depraved that they practice polygamy. So this statement is false. This is false. While our first statement is true. And the only difference between these two statements are that we have swapped the order of the quantifiers. Again, note that the point that I am making here is that the order of the quantifiers matter. Whether you say for every M in the set Charles, Philip, William, there exists a W in W, that is different to saying that there exists a W in W, so that for every M in Charles, Philip, William, that is different. Okay, so here, the point that we are making here, the order of quantifiers matter. Okay, so now we have gone through a little example, let's say like a real world, or an example based in reality, of how quantifiers and quantified statements work. And also, very importantly, what you should remember, if you have not encountered it before, the negation of an implication is not another implication. It is an AND statement. Okay. So I'm going to end this video here. I will see you in the next one.